Hi everybody, welcome back to the Feynman technique. Here's another integral I got off the internet somewhere. We're going to be using a few techniques to solve it. We're going to be using integration by parts. We're going to be using the Leibniz rule for differentiation under the integral sign, aka Feynman integration. We'll be using Taylor series expansion. Alright, so let's get started. First thing we're going to do is we're going to use the DI method to use integration by parts on that. So we will be taking the derivative of the natural log of e to the x plus 1 over e to the x minus 1. And we will be integrating dx. Alright, well, what will this give us? Well, let's see. We're going to get 1 over the inner function, so that will be e to the x minus 1 over e to the x plus 1 times the derivative of the inner function, which is, let's see, we're going to have this squared in the denominator, so that's going to be e to the x minus 1 squared, and then we'll have e to the x times e to the x minus 1, and then minus e to the x times e to the x plus 1. Alright, right away we can see this and that will cancel. Alright, and this on the top, well, let's see, we could factor out an e to the x, and then inside we would have, let's see, e to the x minus e to the x, and then negative 1 minus 1, or just negative 2. So that will just give us negative 2 e to the x. I did that right? Alright, we factor out the e to the x, then this becomes e to the x minus e to the x, and then minus 1 minus 1, or negative 2. Alright, so all in all, this is going to give us minus 2 e to the x over this times this, which is e to the 2x minus 1. And of course, this will just give us x. Alright. So what does that give us for I? Well, that's going to give us this times this from 0 to infinity. And then plus 2 times the integral from 0 to infinity. Don't forget this is a plus and then a minus. So we have 2 times the integral from 0 to infinity of x, e to the x over e to the 2x minus 1 dx, right? Yep, we have this times this evaluated from 0 to infinity, and then minus and minus is a plus. Bring out the 2, we have the e to the x, we have the x, we have the denominator, we're good. Okay, so right now let's try to see what happens if we put in these bounds. Well, let's see. This is going to become, let's see, the x is going to become infinity, and the natural log expression is going to become infinity over infinity, which is just 1 in this case. In this case, it's 1. The limit of this expression as x approaches infinity is 1. So we have natural log 1, which is 0 times infinity. So it's we'd have to use L'Hopital's rule. And then likewise for 0, we'd get 0 times, let's see, e to the x plus 1, that'd be 2 over 0, which is infinity. In other words, we'd have another, we'd have a 0 times infinity, which would allow us to use L'Hopital's rule again. And when we do that, we're going to find that all those limits just go to 0. I'm not going to show that on the board. It is true, though. All right, so this is what we're left with. Okay, so now let's make the substitution u equals e to the x. Therefore, du is equal to e to the x dx, but this is just u, so that's du over u equals dx. All right. So that's going to give us I equal to 2 times, well, let's see, e to the infinity is infinity, e to the 0 is 1. Let's see, our x is natural log u. Our e to the x is u. Our e to the 2x is u squared. The minus 1 is still a minus 1. And the dx is a du over u, which will cancel the u in our numerator right there. All right. So now it's time to remember this, that the sum, as n goes from 0 to infinity, of x to the 2n is equal to 1 over 1 minus x squared on negative 1 to 1. Actually, I believe in this case they are included, although it wouldn't matter because we could just use a limit. And I may have gotten that wrong, so don't take my word for that. I am terrible at remembering convergence. Let's see if I can figure it out really quick in my head. Let's see, if we had a negative 1, this would just add up to infinity, which would match here. Yeah, that'd be good. But what about 1? 1 would add up to infinity as well. And 1 here would, yeah. So I believe both bounds are included in this case. Like I said, it wouldn't really matter since we just take a limit anyway. All right. Yeah, so we just need to know that that's true. But that doesn't help us yet, because we actually, you'll notice that our bounds right here are not, they don't match with these. So we need to somehow get our bounds of integration to go from negative 1 to 1, or be somewhere in that interval. So we'll make another substitution that w is equal to 1 over u, therefore dw, or I should say du is equal to negative 1 over w squared dw. There we go. All right, so that's going to give us this. We'll still have the 2. Let's see, the integral going from 1 over 1 is 1. 1 over infinity is 0. This would become natural log of 1 over u. This would become u to the negative 2 minus 1, and then we'd have a factor of, I'm sorry, these should all be w's. W. Negative 1 over w squared dw. All right. First, let's distribute this w squared. That'll make this a 1 and this a w squared. All right. And then let's distribute this negative sign. And we'll have it cancel with the negative sign that would come from flipping this. So we got rid of a negative sign here. We flip this, introducing a negative sign that will cancel with that one. So that's still good. All right. Well, let's switch the order of these two things and then switch our bounds. There we go. All right. So now we can start to utilize this fact. But first, let's create a function of t that's equal to the integral going from 0 to 1 of x to the t over x squared minus 1 dx. All right. Well, that's going to be equivalent to if we use this. If we replace our 1 over 1 minus x squared with this, let's see, what's that going to give us? Well, hey, let's do this. Let's make this x squared minus 1 and put a negative sign in there. There we go. All right, so, all right, that's just going to be equal to the integral going from 0 to 1 of x to the t times the sum as n goes from 0 to infinity of x to the 2n, and we'll have a negative sign, and then dx. So this will become, let's see, 2n plus t, and then we could switch the bounds of integration and summation. So let's just make this x to the 2n plus t. Then we bring the sum on the outside. There we go. All right. So this is just going to become x to the 2n plus, or this is just going to become 1 over 2n plus t plus 1. Yep. The evaluation of this integral is 1 over 2n plus t plus 1. So we'll just put that right in the sum. 1 over 2n plus t plus 1. And I think I did that right. It was kind of a messy explanation, but if you rewind the video, you should be able to follow it. But you can get from here to here using this. And if you didn't follow my explanation, try to work it out yourself. You can get from here to here using this. All right. Well, how does that help us? It doesn't right now. But using the Leibniz rule for differentiation under the integral sign, on this part, we get f prime of t is equal to the integral from 0 to 1 of x to the t natural log x over x squared minus 1 dx. And that will be equal to the derivative with respect to t of this sum right here. And that's easy to evaluate. That's just the derivative with respect to t of the inner function there. All right, so that's going to be negative sum as n goes from 0 to infinity of, well, let's see. Actually, we're going to recover a negative sign by taking the derivative, so it will become a positive. And now we're going to have 1 over 2n plus t plus 1 all squared. And a quick note, these things don't converge. It's kind of important to note that we don't actually need this to converge because we're not actually interested in f of t. We are interested in f prime of t, and I'll show you why right now. The reason we're interested in f prime of t is because you'll notice that if we let our f prime of t, if we evaluate f prime of t at the point t is equal to 0, what do we have? We'll just have the integral from 0 to 1 of natural log x over x squared minus 1. And that's almost what we want. We're just missing that 2. So in other words, we can say that 2 times f prime evaluated at the point 0 is going to give us the answer that we want. So that means that I is simply equal to 2 times this thing, where t is equal to 0. So that means that I is equal to the sum as n equals 0 to infinity of 1 over 2n plus 1 all squared. Well, actually, it's equal to 2 times that. All right, and this I evaluated in a previous video. This is the sum of the reciprocals of the odd squares. The sum itself evaluates to pi squared over 8. So 2 times that evaluates to pi squared over 4. And that is it. That's the answer. I hope you enjoyed that.